we now begin dynamics. For those of you enrolled in Conceptual Physics AB, it's just merely the next unit. For those of you enrolled in Physics AB, this covers chapters 4 and 5. For those of you enrolled in Honors Physics AB and AP Physics C, this covers chapters 4 through 6. Recall that mechanics, the study of motion, is divided into two parts. First of all, we covered kinematics in the previous unit. Kinematics is concerned with the mathematical description of motion. Now, at no time during that unit on kinematics, however, did I say a word about what causes such motion. That's what we begin today with dynamics. Dynamics is concerned with understanding the causes of motion. Let's briefly revisit, however, the ancient Greeks. According to the ancient Greeks, the study of motion can be summarized into three statements. The first of those statements is what's called the geocentric universe. The Earth is at the center of the universe, and all celestial motion that we see in the sky is perfectly circular and centered on the Earth. For those of you that are not enrolled in AP Physics C, you've already seen that that statement is entirely incorrect. That ultimately culminated with the discovery of Kepler's laws of planetary motion. For those of you that are enrolled in AP Physics C, you'll actually see that material later on in this unit. Okay, and then we come down to the surface of the Earth. With regards to motion near the surface of the Earth, we have the following two statements. The first of those statements is heavier objects fall faster than lighter objects. We saw in our unit on kinematics through Galileo's experimentation that that statement is incorrect. Galileo discovered that all objects, regardless of their weight, in the absence of air resistance, fall with the same constant acceleration due to gravity, of 9.8 meters per second squared. And then secondly, with regards to motion near the surface of the Earth, we also have the following statement. I stated this back at the beginning of the previous unit, but I haven't said anything about it since. According to the ancient Greeks, all moving objects eventually come to rest. It was thought by the ancient Greeks that there was something special about an object being at rest. They referred to it as the object's natural state. Okay, so we have this statement. Once again, according to the ancient Greeks. According to the ancient Greeks, all moving objects eventually come to rest. Once again, it was thought that there was something special about an object being at rest. The ancient Greeks referred to it as the object's natural state. The object's natural state is that of rest. Now recall that the ancient Greeks reached their conclusions based upon just simple observations. They never did any experiments. They thought that it was just good enough to observe the natural world around you and then draw conclusions based upon your observations. So if you observe moving objects around you in the everyday world, it's easy to reach this conclusion. Because, for example, you take an object, say, and drop it vertically like so, it eventually comes to rest. Take an object and toss it as a projectile, like so, it eventually comes to rest. Take an object, say this cart or glider, and slide it horizontally across a surface like so. It eventually comes to rest. So once again, it's very easy to reach this conclusion. Now, as I did this last simple demonstration, you may have been saying to yourself, well, very simply, it was just friction that was slowing down the object. You're, of course, entirely correct, but the first person to make that realization was Galileo Galilei in the 17th century. Galileo realizes that, like air resistance, the force of friction slows down moving objects. Now, before I go any further, I said the word force. Let me describe exactly what is meant by that word. Okay, force, very simply, is a push or a pull that's exerted upon an object due to an external agent. In other words, due to something else. A push or pull that is exerted upon an object due to an external agent. 'Okay, 'External 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 agent. 'Okay very simply, Galileo realizes that like the force of air resistance, the force of friction slows down moving objects. So we jump immediately to the 17th century. Galileo realizes that like air resistance, there we go, the force of friction slows down moving objects. So now Galileo asks and answers the following question by designing an experiment. The question very simply is this. Okay, well, what would happen to a moving object in the absence of friction? What would happen to a moving object in the absence of friction? So to answer this question, Galileo designs a simple experiment. His experiment is actually just a slight extension, if you will, of the original experiment that he did that I described in kinematics, for example, that led to the discovery of free fall, acceleration due to gravity. Here's basically, however, what he did in this experiment. Okay, like in his first experiment, he took an inclined plane and he tried to make it as smooth as he possibly could. So he tried to mimic a frictionless surface. As we'll see later on in this unit, there's actually no such thing as a frictionless surface, but Galileo tried to envision one as best he could. So he approximates a frictionless surface. Okay, now think of this as a ramp, and what he does here is he actually extends the ramp out to the right-hand side. Basically something that looks like this, and then once again the whole thing here is mimicking a frictionless surface. And now very simply he does the following. He takes an object, he sets it on the left-hand side of my diagram, takes that object, sets it there, and releases the object from rest. Okay, so here's an object like so. And the object is released from rest. Okay, now let's immediately jump to his experimental result. His experimental result is that regardless of the shapes of his ramps, the object always returned to its original height. Regardless of the shapes of his ramps, the object always returned to its original height. So then therefore, as I've drawn it, if I then release the object from rest, it returns to its original height over here like so for an instant prior to moving back down to the left-hand side. This occurs regardless of the shapes of the ramps. So imagine, for example, on the right-hand side, a shallower ramp, something like so, for example. Okay, in this case, the object will travel ultimately a greater distance from here to here as it would from here to here, but the result is exactly the same. Regardless of the shapes of the ramps, the object always returned to its original height. Now let me show you a slightly different version of Galileo's original experiment. I'm not going to do so by using frictionless ramps. Instead, I'm going to do so by using a pendulum. In order for you to see this, however, what I have to do is I have to tilt my phone. Yes, I use my phone as a camera. Okay, so bear with me here for just a few moments. Let's just make sure I can do this without dropping my phone. Okay, there we go. Okay, so right here is a pendulum. And now what I'm going to do is I'm just going to draw the pendulum up like so to my chin, and then I'm going to release the pendulum from rest. And then lo and behold, the object returns to its original height. Here it is once again, like so. Okay, let me go ahead and move my camera back. Once again, without dropping my phone. There we go. Okay, now Galileo didn't understand why the object would always want to seem to return to its original height. Our full understanding of that didn't come until well after Galileo's death. However, Galileo realized that his experimental result had an implication. Let me do some erasing. Okay, let me phrase the implication of Galileo's result as a question. What would happen if the right-hand side of the ramp on my diagram, what would happen if the right-hand side of the ramp was horizontal, frictionless, and infinitely long? What would happen if the right-hand ramp was horizontal, frictionless, and infinitely long? So imagine the following, like so. And then what we do is we take our object like so, we set it here at rest on the left-hand side. Once again, the whole thing is thought of as frictionless. And then right here, we'll use this dotted line to indicate the original height. Okay, and then once again, we release the object from rest. So then therefore, what's going to happen to the object when it gets here to the right-hand side like so, and it's moving horizontally with some speed? Well, if the object is always trying to return to its original height, regardless of the shapes of the ramps, on the right-hand side, this then means that the object will continue to move at a constant speed in a straight line forever, trying to return to its original height. The object will move at a constant speed in a straight line. Now, by the way, when I say constant speed in a straight line, what I'm specifically meaning is constant velocity. An object will move at a constant speed in a straight line forever, trying to return to its original height. So then therefore, is it natural for a moving object all by itself to just eventually come to rest? Once again, that's according to the ancient Greeks. No. So Galileo's experimental result in realizing its implications, that is, what can he conclude from his experimental result, is that an object will continue to move at a constant speed in a straight line forever, in this context, trying to return to its original height. What Galileo discovered here is a fundamental law of nature. As I begin to describe this fundamental law of nature to you, keep in mind that this is not a definition. Galileo discovered this fundamental law of nature, and as we'll see, it begins to form the entire basis of understanding the causes of motion. Okay, let me do some erasing here. Okay, what Galileo discovered here, this fundamental law of nature, has a couple of different names. It's called the law of inertia. It's also sometimes referred to as Newton's first law. Okay, let me state the law of inertia in the following way. Once again, this is not a definition. We're recognizing a fundamental aspect of nature. An object will move at a constant velocity. Unless acted upon by a, and for now I'm going to leave a blank space here that will fill in at a later date, but for now an object will move at a constant velocity unless acted upon by a force. Okay, now let me show you a more modern version of Galileo's experiment illustrating the law of inertia. I'm going to do so by using this device that I have here at my desk, which is called an air track. It basically works exactly the same way as a two-dimensional air hockey table does. In this case, however, the motion is one-dimensional. Now, underneath my desk, I have an air source. And the air source then, by means of this tube, blows air into the air track. And then along the surface of the air track, here are a series of holes. The air then comes out through the holes, and that then provides a cushion of air for this cart or glider to glide upon. So it basically works the same way as an air hockey table does, except in this case it's just one-dimensional. Okay, now before I turn the air on and friction is present, as soon as I let go of the object like so, the force of friction immediately causes it to slow down and it comes to rest. However, when I turn the air on, I then therefore remove the force of friction. Once again, it doesn't provide for us exactly a frictionless surface. There's no such thing. However, over a distance of just a few feet or a few meters, it does a nice approximation of a frictionless surface. The air source is a little loud. Like so. So after I release the object, I am no longer exerting a force on it, and then therefore if the air track is horizontal, frictionless, and infinitely long, then after I release the object will move at a constant velocity, a constant speed in a straight line, forever, unless acted upon by a force, in this case the other end of the air track. Once again, what Galileo has discovered here is a fundamental law of nature. Okay, now let me ask you the following question. Based upon the law of inertia, is there any physical difference between an object at rest and an object moving at a constant speed in a straight line? The answer to that question is no. There's no physical difference between the two because both are at a constant velocity. An object at rest is just merely at a constant velocity of 0. There is no physical difference between an object at rest and an object moving in a straight line at a constant speed. Both are at a constant velocity. An object at rest is just merely at a constant velocity of 0. Okay, now in the next part of the lecture, with no mathematics whatsoever, we'll get to that a little bit later on, we could actually now qualitatively explain all sorts of different aspects of motion using the law of inertia that the ancient Greeks would have struggled to explain. We'll get to that in the next part of the lecture.